Hello friends, welcome back to this series on statistical mechanics. In this episode, we will be dealing with one of the major concepts in the development of statistical mechanics, which is called the Gibbs paradox. In the previous episode, we have computed the value of the number of microstates in a classical ideal gas as equal to omega, which is equal to V by h cube raised to 3n 2 pi mv raised to 3n by 2 divided by 3n by 2 factorial. So, this is the total number of microstates for a classical ideal gas. Now, with this one, starting with this number of microstate, we can write down the expression for the entropy of a classical ideal gas using the expression S is equal to KLN omega. This is an expression which was originally proposed by Boltzmann. So, we substitute this expression over here. So, is equal to K n ln. So, we have to do the logarithm of the raised to n, which means that we have brought down the n into the normal terms. So, ln V by h cube. So, let me jump over one step and make it simplified to write it as 4 pi mu divided by 3n raised to 3 by 2 plus 3 by 2 nk. For those students who want to really reach this expression from here, let me suggest you to utilize the Stirling's formula. What is Stirling's formula? It is a mathematical expression. Ln of n factorial is equal to n ln n minus n. Ln n factorial is equal to n ln n minus n. So, this is the famous Stirling's expression. So, I have naturally used this kind of an idea in this simplification process. So, the output is that we have computed the expression for entropy of a classical ideal gas based on our evaluation of the number of microstates. So, this is this should be a major expression in the development of statistical mechanics and the discussions which are now coming in for the rest of this series. Because of its critical importance, one should be evaluating its applicability and its accuracy in different situations. One should always remember that one of the assumptions which we made was that we have a classical ideal gas. Classical means naturally I will assume that the particles are identical and then the particles to be distinguishable. So, all these assumptions are built into this expression and its evaluation. Now, we have one of the things which we have to do for any kind of physical parameter, whenever it is being a new expression is being brought into attention, is its categorization it into different kinds of parameters. In physics, we have this categorization of the physical parameters into extensive parameters and intensive parameters. Extensive parameters and intensive parameters. So, how do they distinguish with each other? Extensive parameters are those parameters which changes or which scales depending on its change in the size. Okay. Whereas intensive parameters are those parameters which does not depend on the change in the size. For example, the extensive parameters I can tell the values like mass, volume, thermodynamic quantities I can have enthalpy or even entropy or Gibbs free energy or Helmholtz free energy, etc. These are all quantities which we can classify as belonging to extensive parameters. So, intensive parameters are those parameters which does not depend on the size of the vessel or the size of the matter on which we do the experiments. For example, your melting point or the temperature, the temperature, the value of the temperature or the hardness of a material, right, like Young's modulus or what are values. So, all these parameters can be considered to be intensive parameters, that the parameters which does not depend on the size of the particle. Now, as I have listed here that entropy should be an extensive property. Now, since we have found out a new expression for the entropy for the classical ideal gas, we should check if our expression really obeys the extensive property of a physical of any physical quantity such as entropy. So, how do we check that? In the expression for the entropy, S is equal to Nk ln V by H cube S cube 4 pi Me divided by 3n raised to 3 by 2. Let me put a square bracket here, plus 3 by 2, right. Unlike our previous slides, I have just taken the Nk outside. So, that is why this 3 by 2, instead of 3 by 2 Nk, now I have written 3 by 2. So, now this is the expression for the entropy which we have calculated. So, if the entropy has to be an extensive parameter, if I multiply the entropy with x, which means that if I change the size of my vessel to x times, my entropy should naturally get multiplied by x, which means that my final S has to be x times the initial s. So, that is the then only it will be an extensive parameter, right. If I need to check that, I need to utilize this expression, which means that definitely I need to consider that n is equal to x n, E is equal to n E, and V is equal to, sorry, not n, sorry, x e, V is equal to x v. So, let us substitute these multiplication factors into our this expression. Okay. So, let us utilize that. Therefore, my new expression for x, s will be, s is equal to x n k ln x v divided by h cube 4 pi m x e divided by 3 n x n raised to 3 by 2, right, plus 3 by 2. So, basically I have substituted all these expressions into this expression and I reach this expression. Now, what should I get? This should be x into x. So, let us check if it is obeying that way. So, these two x's, x will get cancelled out, which is okay for me, which makes it correct, and I have this x over here, which is anyway needed to make it x into s, but the problem is that now I have an additional x over here. So, this x is an additional quantity over here, which means what? Which means that my s will not be equal to x into s, or s of not equal to the multiplication of the initial entropies, which means that this kind of a test suggests me that the entropy which I evaluated for a classical ideal gas is not a extensive quantity, which is not acceptable, which gives me a clue that my evaluation of the entropy could be wrong. In any case, since this is a major expression, it is always good that we re-evaluate it, evaluate the applicability of the extensive quantity or extensive property with another test. So, now let us check the validity of this extensive property using something else called the entropy of mixing. For the purpose, we will keep this expression over here. So, let us start with this one. So, what we are going to do is that we are going to apply the entropy of mixing. So, entropy of mixing means that if I mix say n number of constituents, I should be getting the final entropy to be equal to summation of all the initial quantities, right. S is the final S of should be equal to summation over Si. So, that is the idea which I am trying to check here. So, what should I do? Basically, I should be writing down separate expressions for S1, S2 and then add it together and try to see if I get the final one. But before that, let's get into let's make our this this expression for entropy into a more mathematically friendly expression, so that we can apply something like this in a more easier manner. So, for that purpose, what I will do is that so now we have nk ln v into h cube 4 pi m e raised to m e by 3 n. Let us take the nk outside and do some simplifications. So, nk ln v plus nk ln 4 pi n u by 3 n raised to 3 by 2. I can of course take the h inside, which will not affect my expressions over here. Only thing is that I have to put an h squared here, right, 3 n h squared for 4 pi m. Instead of E, I have put u here, because you know I have limited my energy into a sphere of radius u. So, the ln plus 3 by 2 nk. Now, on further substitution, further simplification, I can write it as nk ln v. So, now let us substitute make this more simplified by taking 3 by 2 nk. So, this is ln some quantity raised to 3 by 2, which means that I can naturally take this 3 by 2 over here. So, 3 by 2 nk. So, I have now two terms which are having 3 by 2 nk here, this one and this one. So, let us take that into a bracket, 3 by 2 nk into 1 plus ln 4 pi mu divided by 3 n h squared. Right. Yeah. So, now another thing which we need to do is that since this is a classical ideal gas, we can straight away substitute the expression for the energy of a classical ideal gas. So, what is that expression? U is equal to 3 by 2 nk T. U is equal to 3 by 2 nk T, which I will substitute over this expression. On substitution, I will get it as the expression for S is equal to nk ln v plus 3 by 2 nk into 1 plus ln 4 pi m by 3 n h squared. We substitute for u and write it as 3 by 2 nk T, right. Right. Yeah. So, if you want, you can, of course, you can put a bracket over here just to tell that the ln is applicable to all these terms inside over here. So, on simplification, I can write it as nk ln v plus 3 by 2 nk into I just make the simplifications over here into 1 plus ln 2 pi m k, n got cancelled over here, the 2 and 2 cancel, 2 pi m k divided by s squared, right. Yeah. So, this is the expression for the entropy, yeah, which we can write it as n k ln V plus 3 by 2 n k into 1 plus ln, we make the cancellation of the 3, 2 and 4, and therefore, I can write 2 pi m k t, we have cancelled the n's over here, and 2 pi m k t by h squared yeah. So, this is the expression for entropy of the classical ideal gas, which is actually the same expression, which is another expression for the entropy which we have written earlier. Only thing is that now we have made it more mathematically simpler, and we have applied the expression for the energy of a classical ideal gas. Now, we will go back to our original idea of checking it with the entropy of mixing. So, what we are going to do is that we will take say two boxes where we have two independent boxes where the ideal gases are filled. So, the first box and the second box. The first, we will calculate the entropy for the first box, we will calculate the entropy for the second box, we will mix them together and see if the final entropy is equal to the sum of the entropies of the first box and the second box. So, that is how we check the entropy of mixing. So, that is what we are going to do. For the purpose, what we will do is that we will write down the expressions for S1 and S2. Okay. So, we will start with this expression. So, S1 I can write it as N1 K ln V V1 plus 3 by 2 N1 K into 1 plus ln 2 pi M1 K T divided by h squared right. So, basically both the boxes, the first, this is the entropy for the first box. So, for the first box we have a number of particles N1, volume V1, and the gases are different. So, we have the different masses M1 and the M2. So, here we have M1, and correspondingly I can write down the expression for S2 also, the second box also, into K ln V2 plus 3 by 2 N2 K into 1 plus ln 2 pi M2 KT divided by S squared, right. So, what is the experiment? I mix the two boxes, which means that for the new box, naturally my volume has to be the sum of the two volumes. That means V1 plus V2 has to be V. Okay. Otherwise, I cannot ask the experiment to be extensive parameter. I cannot check that quantity. So, the first and foremost, I should accept this fact that V1 and V2 should be equal to a new volume V. So, that the volume of my new box should be equal to this one. And also, since these quantities are getting repeated, for my mathematical convenience, I will take this quantity as equal to a quantity called the alpha I. So, alpha I is equal to 1 plus ln 2 pi mi kt by s squared. Okay. So, alpha I, so these are the two assumptions, V1 plus V2 is equal to V and alpha I is equal to this one. So, now I am going to apply these two simplifications and into this expression and check if my final entropy is equivalent to the initial mixing of the two boxes. So, we have this expression for the S1 and S2 and I have already talked about the value of the alpha. So, instead combining these two, that means summation over Si is equal to S1 plus S2. I can write the expression as S1 plus S2 N1 k ln V1 plus N1 k ln V1 plus N2 k ln V2 plus 3 by 2 k into this quantity we have made it simplified it into as alphas, right. So, alpha I. So, 3 by 2 k into N1 alpha 1 plus N2 alpha 2. Okay. So, this is the expression for the mixed box. Now, we need to calculate what will be the corresponding entropy for an equivalent box in which there will be double number of particles, N1 plus N2 number of particles and the volume V1 plus V2. I can write the expression for SF as equal to N1 plus N2 into k ln V plus 3 by 2 k into N1 alpha 1 plus N2 alpha 2. Right. Now, it is very clear that these two expressions are not same, right. So, N1 k ln V1 plus N2 k ln V2 is not equal to N1 plus N2 into k ln V. They are entirely different, or if you need me to exactly write an expression for the differences between the two, I can write SF minus sum over Si is equal to k into N1 ln V by V1 plus N2 ln V by V2, right. So, this is the expression for my the difference between SF and the sum over Si, which is not equal to 0, or my delta S is greater than 0, which is not acceptable for a quantity like entropy, which is supposed to be a extensive quantity. So, this is what we call as the famous Gibbs paradox. So, that is it. So, here we end this episode. The more aspects of Gibbs paradox and how we solve the Gibbs paradox, we will discuss it in the next episode. Thank you.